Hello all, welcome back to the session. So we're going to continue with emerging trends, JMAG in new age engineering with another novel topic from Maged Ibrahim from NRC, National Research Council. Just to give a brief overview, background of Maged, Maged Ibrahim has over 8 years of experience in design and modeling of electric machines. He received his master's and PhD degree from Concordia University in 2011 and 2014. From 2015 to 17, he was an assistant professor in the Department of Electrical Engineering at Forest University in Alexandria, Egypt. In 2018, he joined the National Research Council of Canada, where he's currently working on the design of 3D electric motors using additive manufacturing. With this, I will go ahead and stop sharing my screen and welcome Maged onto the screen.
Hello, everyone. Thank you, Bert, for the introduction, and thank you for inviting me to the user conference. So today I'll be presenting our work on the design and optimization of a permanent magnet machine using cold spray additive manufacturing. So the presentation, first I will introduce the technology of cold spray additive manufacturing, and then I'll go through a new design that we have developed that utilizes this technology. Last year we presented the results for this design, but we didn't have a patent filed at this time. But this year, since the patent has been filed, we will also present the full design and results. Then we will optimize the motor for an electric vehicle traction drive and compare it to a commercial electric vehicle motor. So as the previous speakers also illustrated, there is also an increasing demand on electrification of transportation, ranging from electric vehicles, aerospace applications, and this also poses strict requirements on electric machines. This requirements ranges from having high efficiency, high reliability, and also small size and weight, minimized noise and vibration, and finally, reduced cost is also very important, especially for mass production products. And FEA also plays an important role in the design and optimization of these motors, not only the optimization using the electromagnetic simulations, but also it becomes essential to use thermal and structural analysis, since these motors tend to operate at higher temperatures and also higher operating speeds. So the optimization has to take care of these 3 simulations simultaneously to make sure that you end up with an optimum design. So if we look at the conventional fabrication methods of electric motors, usually you start with a cold rolled silicon iron sheets that are reduced to a specific thickness. Then the sheets are stamped, as you can see here, to the dimensions of the stator core. And then the individual laminations are stacked one after the other to form the whole stator core that is bonded. Then insulation and windings are inserted to form the stator. The same process is also repeated for the fabrication of the rotor core. And instead of using windings, of course, for permanent magnet machines, you use a permanent magnet that is that you place on the rotor surface using adhesive material, with or without having carbon fiber sleeve at or another retaining sleeve at the rotor surface. If it's an interior permanent magnet, then you insert the magnets in the cavities inside the rotor core. So as you can see from this slide, the process of fabricating motor, it takes many fabrication steps, and this increases the manufacturing cost. And also this limits the possible motor designs, because with laminations, the flux has to flow in the plane of the lamination. So mostly motor designers are limited to 2D designs. And this also limits the possible designs that you can achieve. At NRC, we developed a new method for fabricating soft and hard magnetic materials. It's called cold spray additive manufacturing. So with cold spray additive manufacturing, you start with powders of magnetic material that can be soft or hard magnetic material, along with the binder material. These two powders are mixed together, and using high pressure gas, they accelerated using a cold spray tool, and then it gets sprayed through a nozzle at very high speeds. So when the powder hits the receiving structure at this high speed, the bonding material tends to get deformed, and it basically the whole powder sticks onto the receiving structure. So by controlling the movement of the spray tool and controlling the movement of the receiving structure, you can actually have full control of the shape that you can produce using the cold spray process. So here in this slide, you can see some examples of permanent magnets and SMC that we have fabricated using the cold spray process. So you can see that you have quite complex structures ranging from spiral permanent magnets on an inner cylinder to hourglass shaped permanent magnets with SMC to permanent magnets with different thickness. So this manufacturing methods allow you to fabricate magnetic structures that would be very difficult to make using conventional methods. And also it doesn't require many steps to fabricate the final prototype. Like with laminations, you need to have several steps until you reach your final core or final prototype. But here, it's just the process of programming the spray tool and programming the movement of the receiving structure, and you have no assembly, almost no assembly in the process. And also, since we are using isotropic permanent magnet and isotropic SMC core, we can actually allow a 3D designs that can take advantage of various design options. And also the cold spray magnetic materials, they tend to have high mechanical and thermal properties, and this can allow you to achieve high mechanical strength structures, and at the same time you can dissipate the generated heat easier than conventional materials. And compared to other additive manufacturing methods, the cold spray process can actually achieve quite high build-up rate, up to several kilograms per hour. And this is very important, especially for mass production of electric motors. Of course, one of the challenges of this design is that it tends to have lower remnant flux density compared to conventional magnets. So for example, the NRC fabricated cold spray magnets, they have a remnant flux density of around half a Tesla, while conventional magnets, they can easily exceed 1.2 Tesla. But at the same time, we are only using isotropic powder, magnet powder. So if we compared the NRC magnets with other isotropic magnets, like bonded magnets or magnets fabricated with other additive manufacturing method, we can see that we have comparable remnant flux density. That is not very far from the isotropic powder limit. And also the coercivity of the magnet is not affected by much with the cold spray process, so the demagnetization is relatively stable. But the main advantage of the NRC magnets, cold spray magnets, is that it has much higher mechanical strength compared to other magnets. So on the right figure, you can see that the ultimate tensile strength of the cold spray magnet exceeds 200 MPa, and compared to other permanent magnets, it is much stronger, and this can allow you to operate the motor at higher speeds. So to take advantage of this technology, we started our investigation with a conventional synchronous reluctance motor. So these motors are used in many applications right now, mainly because they can reduce or eliminate the rare earth magnets. But one of the main limitations of this design is that you need to have bridges and center posts basically to hold the rotor structure together. These bridges and center posts are very important to increase the mechanical strength of the motor at high speeds, but they also, when you use larger bridges or larger center posts, you also increase the leakage flux of the motor, and this tends to reduce the motor saliency and also reduce the motor output torque. So for example, when you apply Q-axis current, the bridges and basically the barriers here should be able to reduce or limit the Q-axis flux, which could happen if you have no bridges or center posts. But since you have these bridges, you can see that you have high leakage flux in the bridges and also some leakage flux in the center posts. And this tends to affect the motor saliency, which is basically the ratio between LD and LQ. So you can see that the difference is compromised because of the bridges, but at the same time also the saliency is reduced at low loading conditions, mainly because you have partial saturation in the bridges, so you lose your saliency, and this tends to greatly affect the performance, especially at low current conditions that are utilized at high speeds, low torque conditions. So we tried to look at the effect of removing the bridges and center posts. So we created a hypothetical design where you have basically no bridges, no center post, and the rotor would be consisting of separate segments of soft magnetic material that are separated by air. Of course, this design, it's impossible to fabricate, but we just want to see what would happen if you remove the bridges. So you can see from this figure on the right side that you have slight reduction in LD when you remove the bridges, because you have less amount of steel in the D-axis flux path compared to the original design. But also the most important aspect is that you have very large reduction in LQ. So LQ is basically reduced in less than half, in more than half, but also it's extremely important that LQ becomes unaffected by the armature current magnitude. So with conventional synchronous reluctance, you can see that at low loading conditions, you begin to lose your saliency. But if you simply remove the bridges, then you would have basically very large saliency at most loading conditions. So this tends to also increase the motor output torque, increasing the output torque by 35%, and this is at full load. And at partial load, this percentage will also increase further. So as I said, this design would be difficult to make with conventional methods, but with cold spray additive manufacturing, you can actually fabricate a similar design with layers of SMC and permanent magnet that can be sprayed alternately on the rotor shaft. So you begin with the rotor shaft, you begin to spray layers of SMC, then permanent magnet, SMC, permanent magnet, till you form the whole rotor core. And we used in this design permanent magnet and SMC that are successfully fabricated with the cold spray process. And the elimination of the bridges and center posts in this design would enhance the motor saliency greatly. And at the same time, you are also using permanent magnets in the gaps. So this will give you an additional magnet torque component that also has low leakage flux compared to conventional interior permanent magnet motors. So with the layered motor that we have developed, you gain an additional 35% of output torque compared to the segmented synchronous reluctance motor. So in this figure, we compared the layered motor to different motor configurations ranging from synchronous reluctance, segmented synchronous reluctance, surface permanent magnet motor with remnant flux density of 1 Tesla, and PM assisted synchronous reluctance motor with a remnant flux density of 1 Tesla. And you can see that even though the layered motor utilizes a magnet with almost half the remnant flux density, it still can provide similar or higher output torque compared to the other designs. And this is mainly attributed to the removal of bridges that tend to have lower leakage flux and higher motor saliency. So that was the four-pole design was for prototyping the machine, but we also wanted to investigate the potential of the motor in an electric vehicle application. So we started with a conventional interior permanent magnet motor that's used in Toyota Prius. So this motor, as many of you already know, it's an interior permanent magnet motor with V-shaped permanent magnet. The permanent magnet has a remnant flux density of 1.25 Tesla, and it also uses, of course, steel laminations. And you have bridges and center posts basically to hold the rotor structure together. And the stator is 48 slot stator with distributed windings. And we tried to use the exact same stator with the layered motor. So we used the 48 slot stator with the layered with exactly the same axial length. And the rotor, instead of V-shaped magnet, we used the layered motor structure. So with the layered motor, you have alternate layers of SMC permanent magnets that also forms an 8-pole design. With this structure, we used the 3 layers of permanent magnets. And as you can see on the right figure, the geometry is controlled basically by 6 parameters that defines the angle of each of these arcs at the rotor surface. So these parameters are used to optimize the motor structure. So using JMAG GA optimization algorithm, we optimize the motor structure with an objective function to first minimize the magnet area, which is related to the majority of the rotor cost, and also minimize the weighted loss, which is the ratio between the total loss over the output power. And this is for high-speed low torque conditions, so that you would minimize the loss at highway operation of electric vehicle. We had 2 design constraints. First, that the maximum torque should exceed 200 Newton meter, which is the output torque of the Prius, and also the torque ripple should be less than 20%. So this figure shows the optimization results that we have for the layered motor, with the vertical axis showing the weighted loss and the horizontal axis showing the magnet area. And each of these dots represents one analyzed design. So the green dots are designs that did not satisfy the torque ripple condition. So they are usually designs with high weighted loss. And the red dots are designs that has average torque less than 200 Newton meter. And they are usually designed with low magnet area. And the blue dots are the designs that satisfy all the design constraints. So we basically are trying to minimize weighted loss and magnet area. So we selected several designs at the corner of this region, did several FEA simulations on them, and selected one candidate design that we considered the optimum design for the layered motor. And this is a comparison between the torque of the layered motor compared to the Prius motor. Both of them has similar maximum torque, but you can see that the layered motor has relatively different operating characteristics, especially at high current angles. The layered motor tends to give higher torque. This is mainly because it has higher reluctance torque compared to the Prius motor because of the low leakage flux. So it operates more closer to asynchronous reluctance compared to a permanent magnet motor. And this can give great advantages at high speed operation where high current angles are usually utilized. So we also use JMAG to analyze the efficiency maps of the 2 motors. So as you can see on the left figure, the maximum efficiency of the Prius lies between 4,000 and 6,000 RPM, and the efficiency tends to decrease at high speed, low torque conditions. But with the layered motor, you can see that the high efficiency region is extended between 2,000 to around 10,000 RPM. And the efficiency also tends to improve at low torque, high speed condition. This is mainly attributed to the limited magnet leakage flux that improves the performance in this region. And this is a comparison between the loss of the 2 motors. So at low speed, high torque condition, both designs tend to have similar output, similar loss. So you don't have much loss reduction with the layered motor. But as the speed increases and the torque is reduced, the layered motor tends to have higher loss reduction, ranging from 10, 20, 30, and even higher than 50% loss reduction. And this can be extremely important for electric vehicle application, where at highway you just need relatively small torque and high speed operating condition, and the layered motor can provide significant efficiency improvement in this region. So to make sure that the mechanical strength of the two designs, we did mechanical analysis of the brace and layered motor. So with the brace motor, you have several fine features in the rotor, ranging from the curvature of the bridges and the curvature of the center posts. So these areas are also exposed to high mechanical stress. So to get accurate stress results in this region, we refined the mesh near the edges of the bridges and near the edges of the center posts to improve the calculation for maximum stress in the motor. And you can see here, this is the scale deformation of the motor by a factor of 200. So you can see that the magnets at higher speeds, the centrifugal force tend to push the magnets out. And this, the bridges and center posts, they carry huge mechanical load at high speeds, and this present the weak link of the motor at high speed. The maximum displacement with this motor is around 25 micrometer, which is much lower than the air gap length, so it wouldn't affect the mechanical performance of the motor. But at the same time, the maximum stress in the center posts and bridges exceeds 300 MPa at the maximum motor speed of 13,500. So this represents basically the limitation. This limits the maximum speed of the motor because you have relatively thin features that carry the whole load of the motor at high speeds, and the limitation of maximum speed of the motor also limits the maximum power that you can get out of the motor. We did similar analysis with the layered motor, but since the layered motor doesn't have fine features in the rotor, the results tend to converge with relatively coarser mesh. So you can see that this is the permanent magnet and SMC with mechanical properties obtained using the cold spray process. And since the permanent magnets and SMC both use the same binder material, they would also tend to have similar mechanical properties, and this helps in the mechanical strength of the motor. So this is the result of the mechanical analysis at the same maximum speed of the brace motor. So you can see that the displacement is reduced to around 9 micrometer from 25 micrometer, but the maximum stress in the motor is greatly reduced. So instead of 300, the maximum stress is reduced to less than 50 MPa. But based on our analysis, the weakest points in the layered motor, it's not at the maximum stress. It lies at the interface between the permanent magnet and SMC layer. So when we measured experimentally the adhesion strength between the different cold spray layers, it actually exceeded 70 MPa. And at the maximum speed, the maximum stress in this region is about 22.7 MPa. So you still have a large room for increasing the speed before reaching the maximum adhesion strength of the cold spray process. And you can see this figure compares the mechanical stress of the brace motor to the layered motor. As you can see, the blue line represents the maximum stress of the brace motor. So it's rapidly increases because you have very thin, relatively thin bridges and center posts that tend to have maximum stress areas. So the stress increases rapidly until it reaches the steel yield strength at around 14,000 RPM. And these limits mainly represent the limit for the maximum speed that you can get out of the motor. As for the layered motor, you can see that it has much lower mechanical stress at the interface layer between SMC and permanent magnet. So this stress is much lower than the brace, and it begins to exceed the adhesion strength of the cold spray process at around 24,000 RPM. So this would allow you to easily increase the motor speed by at least 50%. And also the value for cold spray adhesion strength, it can be further improved in the future because we can do further improvements in the material to raise this value higher than 70 MPa. So with this, you can have at least 50% higher speed, and this can also, if it's utilized properly, you can have 50% increase in the motor power density. We also did thermal analysis for the two motors to make sure that the layered motor doesn't have any thermal problems. So we used a simplified structure for the casing with the cooling channels, and you have also end windings with the oil spray cooling, and you have here the shaft, the bearings. And with the layered motor, we used similar structure. The only difference that we reduced the interior permanent magnet motor with the layered motor structure. These are the boundary conditions that we have used for the thermal analysis, with the convective heat transfer from the outer casing to the air of around 10 watt per meter square degree. And for the end windings with the spray oil cooling, it's about, this value is about 25. But most of the heat extraction in the motor comes from the cooling channel in the stator, in the outer casing, with a convective heat transfer of 143. And this is based on ethylene glycol water flowing at 5 liters per minute. Also, we used the contact resistance between the casing, the stator, and the stator laminations, between the magnet and rotor laminations and shaft, and also between the bearings and the casing and the shaft. And we also, based on the fill factor of the stator, we used equivalent thermal conductivity for the insulation layer, and this value is used in the FEA simulations. And as you can see, for the steady state thermal analysis at 25 kilowatt, 3000 RPM, most of the generated heat is concentrated in the coils, and then the stator laminations have also some iron losses, then followed by the magnet eddy current losses and the rotor losses in the motor. And as you can see, the highest temperature, of course, it's in the coils, and you have relatively uniform distribution, temperature distribution in the coil, with about 3-degree difference between the maximum and minimum temperature in the coils. Based on the transient analysis, since both motors have similar output torque, the temperature rise in the coil is similar for both designs. But with the layered motor, you get about 3.5 degree higher temperature in the magnet, and this is mainly because of the higher conductivity of the cold spray magnet that tend to increase the magnet loss, and this causes slight increase in the magnet temperature. And we also did some demagnetization analysis for the layered motor, and the conclusion of this analysis is that you need to appropriately select the NDFE powder grade so that you can avoid a reversible demagnetization of the magnets. This table just compares the performance of the Preus and layered motor. So both of them uses exactly the same 48 slot stator with exactly the same axial length. The rotor core material for the Preus is 0.3 millimeter steel, while the layered motor uses SMC with lower permeability. The rotor magnet and the Preus is centered magnets with a remnant flux density of around 1.25 Tesla, while the layered motor uses a magnet, cold spray magnet, with around half Tesla. The rear earth volume in both designs is similar, and the maximum torque is similar. And the layered motor got the same axial, the same output torque of the Preus motor, mainly because you have higher reluctance torque because you don't have bridges or center posts, and also you have lower leakage flux because of the illumination of the bridges. And the torque ripple is relatively similar in both designs, but with the layered motor, it's fabricated using additive manufacturing. So it's possible also to fabricate a skewed rotor using the cold spray process. And based on the 3D FEA simulations, the skew design would have less than 5% of torque ripple. The maximum efficiency for both designs is relatively similar, with slight improvement in the layered motor, but at high speed, low torque condition, the layered motor tends to give improved efficiency because of its lower leakage flux. But the main advantage that you can get with this structure is its mechanical strength, because you eliminate these thin features in the rotor structure, and the rotor becomes basically a solid piece of steel made of different material that can have much lower mechanical strength. This can allow you to increase the motor speed at least by 50%, so the maximum speed can exceed 20,000 RPM, and this can greatly enhance the motor power density. So in conclusion, the layered motor fabricated using cold spray additive manufacturing can enhance the power density and efficiency of interior permanent magnet machines, mainly because of its low leakage flux and also its high mechanical strength. On the left figure, on the bottom figures, you can see that we started the prototyping process for this motor. As you can see, the base structure is held by an industrial robot. And on the middle figure, you can see this is the first spray layer of permanent magnet that is machined to ensure that the dimensions of the rotor are exact, then followed by another spray layer of SMC, and that is also machined after each layer deposition. We halted the prototyping process for a while because of the COVID situation, but we are planning to resume this the prototyping of the rotor and the testing of the rotor shortly. Finally, I would like to thank JMAG and PowerSys for providing the software that we have used throughout all these simulations. And thank you for your attention, and I would be happy to answer any questions that you have.
Thank you very much, Magad. That was again one very good, insightful presentation. So we do have a couple of questions that came in. I will go ahead and start with the first one here. Is the layered rotor axially or radially segmented?
Well, it's you can consider it axially segmented. So as you can see here, you have several layers. It looks like an axially segmented synchronous reluctance motor, but instead of using laminations that are bended, you are using basically layers of permanent magnet and SMC one after the other.
Okay. Is there some comparison of the power factor between the layered motor and the Prius motor?
Yeah, actually, we did some power factor analysis for both designs. At maximum operating torque, both motors have similar power factor, but at high speed, low torque conditions, the layered motor tend to have better power factor because you don't have that much leakage flux that induces voltage in the motor. So the layered motor tends to have improved power factor at high speed low torque condition.
Right. Thank you for that. Another question is, will it be possible to replace current permanent magnet motors, PM rotors with proposed rotor? Will it be economical?
Of course, at the moment, we are still in the prototyping process, so the process is not optimized yet. But what we are optimistic about is that in the long term, this process is very promising, because if you reach the point where you can automate the fabrication of the rotor, you would greatly reduce the manufacturing steps of permanent magnet rotor, but also you would end up with a motor with improved performance and the potential for having higher speeds, higher power density would be very promising in the future. So I would say at the moment it cannot really replace the conventional designs, but in the future I think it's quite promising approach.
Absolutely, that's really promising to know. So there are a couple of questions. We'll take one more probably. Let's see. Um, for the comparison of the mechanical stress of the layered motor with the Prius motor, is there any adhesion between the magnets and the rotor lamination also assumed for the Prius motor?
When we did it for the Prius motor, we assumed that there is no adhesion between the magnet and the inner part of the laminations, mainly because with time the adhesion tends to diminish because of the centrifugal force that tend to push the magnet out of the rotor. So the mechanical strength of the adhesion tends to diminish with time. So assume that there is no adhesion between the permanent magnet and the laminations. With the layered motor, the adhesion between the two materials is mainly because of the cold spray process. So when you spray one layer after the other, it basically the binder gets deformed and it sticks to the previous layer. So there's no adhesion used with the layered motor.
Okay, that's nice. So one last question, I think with that we can end. So you mentioned that binder controls adhesion and mechanical properties. Does this include thermal expansion of layers? If not, what else needs to be controlled? How do you expect AM to impact rotor lifetime?
That's a very good question. So for now, we didn't consider the difference in thermal expansion of different materials, but I don't think that would be an issue because, as I said, both materials, both layers use the same binder material. So with the similar binder material, we tend to have similar mechanical performance and thermal performance in the different layers. So we didn't analyze the thermal expansion issue yet, but if I would have to guess, I think it wouldn't be a problem. But that's a very important point that we have to address in the future also.
All right. We do have a couple of questions, but Maged, we will facilitate him to answer over the app. But thank you very much for the presentation, and thank you for your time and such an insightful scope of work using JMAG. All right, thank you, and we will start the next session.
Thank you.